Part 1, Chapter 6 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Chapter 6, Instrumental Advances. It is impossible to follow with intelligent interest the course of astronomical discovery without feeling some curiosity as to the means by which such surpassing results have been secured. Indeed, the bare acquaintance with what has been achieved, without any corresponding knowledge of how it has been achieved, supplies food for barren wonder rather than for fruitful and profitable thought. Ideas advance most readily along the solid ground of practical reality, and often find true sublimity while laying aside empty marvels. Progress is the result, not so much of sudden flights of genius, as of sustained, patient, often commonplace endeavor, and the true lesson of scientific history lies in the close connection which it discloses between the most brilliant developments of knowledge and the faithful accomplishment of his daily task by each individual thinker and worker. It would be easy to fill a volume with the detailed account of the long succession of optical and mechanical improvements by means of which the observation of the heavens has been brought to its present degree of perfection, but we must here content ourselves with a summary sketch of the chief amongst them. The first place in our consideration is naturally claimed by the telescope. This marvelous instrument, we need hardly remind our readers, is of two distinct kinds: that in which light is gathered together into a focus by refraction, and that in which the same end is attained by reflection. The image formed is in each case viewed through a magnifying lens, or combination of lenses, called the eyepiece. Not for above a century after the optic glass is invented or stumbled upon by the spectacle maker of Middelburg, 1608, had become diffused over Europe, did the reflecting telescope come, even in England, the place of its birth, into general use. Its principle, a sufficiently obvious one, had indeed been suggested by Mersenne as early as 1639. James Gregory in 1663 described in detail a mode of embodying that principle in a practical shape, and Newton, adopting an original system of construction, actually produced in 1668 a tiny speculum 1 inch across, by means of which the apparent distance of objects was reduced 39 times. Nevertheless, the exorbitantly long tubeless refractors introduced by Huggins maintained their reputation until Hadley exhibited to the Royal Society, January 12, 1721, a reflector of 6 inches aperture and 62 in focal length, which rivaled in performance and of course indefinitely surpassed in manageability one of the aerial kind of 123 feet. The concave mirror system now gained a decided ascendant, and was brought to unexampled perfection by James Short of Edinburgh during the years 1732 to 68. Its resources were, however, first fully developed by William Herschel. The energy and inventiveness of this extraordinary man marked an epoch wherever they were applied. His ardent desire to measure and gauge the stupendous array of worlds which his specula revealed to him made him continually intent upon adding to their space-penetrating power by increasing their light-gathering surface. These, as he was the first to explain, are in a constant proportion one to the other, for a telescope with twice the linear aperture of another will collect 4 times as much light, and will consequently disclose an object 4 times as faint as could be seen with the first, or what comes to the same, an object equally bright at twice the distance. In other words, it will possess double the space-penetrating power of the smaller instrument. Herschel's great mirrors, the first examples of the giant telescopes of modern times, were then primarily engines for extending the bounds of the visible universe, and from the sublimity of this final cause was derived the vivid enthusiasm which animated his efforts to success. It seems probable that the 7-foot telescope constructed by him in 1775, that is, within little more than a year after his experiments in shaping and polishing metal had begun, already exceeded in effective power any work by an earlier optician; and both his skill and his ambition rapidly developed. His efforts culminated after mirrors of 10, 20, and 30 feet focal length had successively left his hands in the gigantic 40-foot, completed August 28, 1789. It was the first reflector in which only a single mirror was employed. In the Gregorian form, the focused rays are by a second reflection from a small concave mirror thrown straight back through a central aperture in the larger one, behind which the eyepiece is fixed. The object under examination is thus seen in the natural direction. The Newtonian, on the other hand, shows the object in a line of sight at right angles to the true one, the light collected by the speculum being diverted to one side of the tube by the interposition of a small plane mirror situated at an angle of 45 degrees to the axis of the instrument. Upon these two systems Herschel worked until 1787, when, becoming convinced of the supreme importance of economizing light necessarily wasted by the second reflection, he laid aside the small mirror of his 40-foot, then in course of construction, and turned it into a front-view reflector. This was done, according to the plan proposed by Lemaire in 1732, by slightly inclining the speculum so as to enable the image formed by it to be viewed with an eyeglass fixed at the upper margin of the tube. The observer thus stood with his back turned to the object he was engaged in scrutinizing. The advantages of the increased brilliancy afforded by this modification were strikingly illustrated by the discovery, August 28 and September 17, 1789, of the two Saturnian satellites nearest the ring. Nevertheless, the monster telescope of Slough cannot be said to have realized the sanguine expectations of its constructor. The occasions on which it could be usefully employed were found to be extremely rare. It was injuriously affected by every change of temperature. The great weight, 2,500 weight, of a speculum 4 feet in diameter rendered it peculiarly liable to distortion. With all imaginable care, the delicate lustre of its surface could not be preserved longer than 2 years, when the difficult process of repolishing had to be undertaken. It was accordingly never used after 1811, when, having gone blind from damp, it lapsed by degrees into the condition of a museum inmate. The exceedingly high magnifying powers employed by Herschel constituted a novelty in optical astronomy, to which he attached great importance. The work of ordinary observation would, however, be hindered rather than helped by them. The attempt to increase in this manner the efficacy of the telescope is speedily checked by atmospheric, to say nothing of other, difficulties. Precisely in the same proportion as an object is magnified, the disturbances of the medium through which it is seen are magnified also. Even on the clearest and most tranquil nights the air is never for a moment really still. The rays of light traversing it are continually broken by minute fluctuations of refractive power caused by changes of temperature and pressure, and the currents which these engender. With such luminous quiverings and waverings the astronomer has always more or less to reckon. Their absence is simply a question of degree. If sufficiently magnified, they are at all times capable of rendering observation impossible. Thus, such powers as 3,000, 4,000, 5,000, even 6,652, which Herschel now and again applied to his great telescopes, must, save on the rarest occasions, prove an impediment rather than an aid to vision. They were, however, used by him only for special purposes, experimentally, not systematically, and with the clearest discrimination of their advantages and drawbacks. It is obvious that perfectly different ends are subserved by increasing the aperture and by increasing the power of a telescope. In the one case, a larger quantity of light is captured and concentrated; in the other, the same amount is distributed over a wider area. A diminution of brilliancy in the image accordingly attends, ceteris paribus, upon each augmentation of its apparent size. For this reason, such faint objects as nebulae are most successfully observed with moderate powers applied to instruments of a great capacity for light, the details of their structure actually disappearing when highly magnified. With stellar groups the reverse is the case. Stars cannot be magnified simply because they are too remote to have any sensible dimensions, but the space between them can. It was thus for the purpose of dividing very close double stars that Herschel increased to such an unprecedented extent the magnifying capabilities of his instruments, and to this improvement incidentally the discovery of Uranus, March 13, 1781, was due. For by the examination with strong lenses of an object which, even with a power of 227, presented a suspicious appearance, he was able at once to pronounce its disc to be real, not merely spurious, and so to distinguish it unerringly from the crowd of stars amidst which it was moving. While the reflecting telescope was astonishing the world by its rapid development in the hands of Herschel, its unpretending rival was slowly making its way towards the position which the future had in store for it. The great obstacle which long stood in the way of the improvement of refractors was the defect known as chromatic aberration. This is due to no other cause than that which produces the rainbow and the spectrum, the separation or dispersion in their passage through a refracting medium of the variously coloured rays composing a beam of white light. In an ordinary lens there is no common point of concentration; each colour has its own separate focus, and the resulting image, formed by the superposition of as many images as there are hues in the spectrum, is indefinitely terminated with a tinted border, eminently baffling to exactness of observation. The extravagantly long telescopes of the 17th century were designed to avoid this evil, as well as another source of indistinct vision in the spherical shape of lenses, but no attempt to remedy it was made until an Essex gentleman succeeded in 1733 in so combining lenses of flint and crown glass as to produce refraction without colour. Mr. Chester More Hall was, however, equally indifferent to fame and profit, and took no pains to make his invention public. The effective discovery of the achromatic telescope was accordingly reserved for John Doland, whose method of correcting at the same time chromatic and spherical aberration was laid before the Royal Society in 1758. Modern astronomy may be said to have been thereby rendered possible. Refractors have always been found better suited than reflectors to the ordinary work of observatories. They are, so to speak, of a more robust as well as of a more plastic nature. They suffer less from vicissitudes of temperature and climate. They retain their efficiency with fewer precautions and under more trying circumstances. Above all, they co-operate more readily with mechanical appliances and lend themselves with far greater facility to purposes of exact measurement. A practical difficulty, however, impeded the realization of the brilliant prospects held out by Doland's invention. It was found impossible to procure flint glass, such as was needed for optical use, that is, of perfectly homogeneous quality, except in fragments of insignificant size. Discs of more than 2 or 3 inches in diameter were of extreme rarity, and the crushing excise duty imposed upon the article by the financial unwisdom of the government both limited its production and, by rendering experiments too costly for repetition, barred its improvement. Up to this time Great Britain had left foreign competitors far behind in the instrumental department of astronomy. The quadrants and circles of Bird, Carey, and Ramsden were unapproached abroad. The reflecting telescope came into existence and reached maturity on British soil. The refracting telescope was cured of its inherent vices by British ingenuity. But with the opening of the 19th century, the almost unbroken monopoly of skill and contrivance which our countrymen had succeeded in establishing was invaded, and British workmen had to be content to exchange a position of supremacy for one of at least partial temporary inferiority. Somewhat about the time that Herschel set about polishing his first speculum, Pierre Louis Guinan, a Swiss artisan living near Chaux de Fonds, in the canton of Neuchâtel, began to grind spectacles for his own use, and was thence led on to the rude construction of telescopes by fixing lenses in pasteboard tubes. The sight of an England achromatic stirred a higher ambition, and he took the first opportunity of procuring some flint glass from England, then the only source of supply, with the design of imitating an instrument the full capabilities of which he was destined to be the humble means of developing. The English glass proving of inferior quality, he conceived the possibility, unaided and ignorant of the art as he was, of himself making better, and spent 7 years, 1784 90, in fruitless experiments directed to that end. Failure only stimulated him to enlarge their scale. He bought some land near Les Brenets, constructed upon it a furnace capable of melting 2 quintals of glass, and reducing himself and his family to the barest necessaries of life, he poured his earnings (he at this time made bells for repeaters) unstintingly into his crucibles. His undaunted resolution triumphed. In 1799 he carried to Paris, and there showed to Lalande several discs of flawless crystal 4 to 6 inches in diameter. Lalande advised him to keep his secret, but in 1805 he was induced to remove to Munich, where he became the instructor of the immortal Fraunhofer. His return to Les Brenets in 1814 was signalized by the discovery of an ingenious mode of removing striated portions of glass by breaking and resoldering the product of each melting, and he eventually attained to the manufacture of perfect discs up to 18 inches in diameter. An object glass, for which he had furnished the material to Cauchois, procured him in 1823 a royal invitation to settle in Paris, but he was no longer equal to the change, and died at the scene of his labours, February 13 following. This same lens, 12 inches across, was afterwards purchased by Sir James South, and the first observation made with it, February 13, 1830, disclosed to Sir John Herschel the 6th minute star in the central group of the Orion nebula, known as the trapezium. Bequeathed by South to Trinity College, Dublin, it was employed at the Dunsink Observatory by Brunnow and Ball in their investigations of stellar parallax. A still larger objective, of nearly 14 inches, made of Guinand's glass, was secured in Paris about the same time by Mr. Edward Cooper of Marcree Castle, Ireland. The peculiarity of the method discovered at Les Brenets resided in the manipulation, not in the quality of the ingredients. The secret, that is to say, was not chemical but mechanical. It was communicated by Henri Guinand, a son of the inventor, to Bontemps, one of the directors of the glass works at Choisy-le-Roi, and by him transmitted to Messrs. Chance, Birmingham, with whom he entered into partnership when the revolutionary troubles of 1848 obliged him to quit his native country. The celebrated American opticians, Alvan Clark and Sons, derived from the Birmingham firm the materials for some of their early telescopes, notably the 19-inch Chicago and 26-inch Washington equatorials. But the discs for the great Lick refractor and others shaped by them in recent years have been supplied by Faye of Paris. Two distinguished amateurs, meanwhile, were preparing to reassert on behalf of reflecting instruments their claim to the place of honour in the van of astronomical discovery. Of Mr. Lassell's specula something has already been said. They were composed of an alloy of copper and tin, with a minute proportion of arsenic, after the example of Newton, and were remarkable for perfection of figure and brilliancy of surface. The capabilities of the Newtonian plan were developed still more fully, it might almost be said to the uttermost, by the enterprise of an Irish nobleman, William Parsons, known as Lord Oxmantown until 1841, when on his father's death he succeeded to the title of Earl of Rosse, was born at York, June 17, 1800. His public duties began before his education was completed. He was returned to Parliament as member for King's County while still an undergraduate at Oxford, and continued to represent the same constituency for 13 years, 1821 to 34. From 1845 until his death, which took place October 31, 1867, he sat, silent but assiduous, in the House of Lords as an Irish representative peer. He held the not unlaborious post of President of the Royal Society from 1849 to 1854, presided over the meeting of the British Association at Cork in 1843, and was elected Vice-Chancellor of Dublin University in 1862. In addition to these extensive demands upon his time and thoughts were those derived from his position as practically the feudal chief of a large body of tenantry in times of great and anxious responsibility, to say nothing of the more genial claims of an unstinted hospitality. Yet while neglecting no public or private duty, this model nobleman found leisure to render to science services so conspicuous as to entitle his name to a lasting place in its annals. He early formed the design of reaching the limits of the attainable, in enlarging the powers of the telescope, and the qualities of his mind conspired with the circumstances of his fortune to render the design a feasible one. From refractors it was obvious that no such vast and rapid advance could be expected. English glass manufacture was still in a backward state. So late as 1839, Sims, successor to the distinguished instrumentalist Edward Troughton, reported a specimen of crystal scarcely 7½ inches in diameter, and perfect only over 6, to be unique in the history of English glass making. Yet at the time the 15-inch achromatic of Pulkowa had already left the workshop of Fraunhofer's successors at Munich. It was not, indeed, until 1845, when the impost which had so long hampered their efforts was removed, that the optical artists of these islands were able to compete on equal terms with their rivals on the continent. In the case of reflectors, however, there seemed no insurmountable obstacle to an almost unlimited increase of light-gathering capacity, and it was here, after some unproductive experiments with fluid lenses, that Lord Oxmantown concentrated his energies. He had to rely entirely on his own invention, and to earn his own experience. James Short had solved the problem of giving to metallic surfaces a perfect parabolic figure, the only one by which parallel incident rays can be brought to an exact focus; but so jealous was he of his secret that he caused all his tools to be burnt before his death. Nor was anything known of the processes by which Herschel had achieved his astonishing results. Moreover, Lord Oxmantown had no skilled workmen to assist him. His implements, both animate and inanimate, had to be formed by himself. Peasants taken from the plough were educated by him into efficient mechanics and engineers. The delicate and complex machinery needed in operations of such hairbreadth nicety as his enterprise involved, the steam engine which was to set it in motion, at times the very crucibles in which his specula were cast, issued from his own workshops. In 1827 experiments on the composition of speculum metal were set on foot, and the first polishing machine ever driven by steam power was contrived in 1828. But 12 arduous years of struggle with recurring difficulties passed before success began to dawn. A material less tractable than the alloy selected, of 4 chemical equivalents of copper to 1 of tin, can scarcely be conceived. It is harder than steel, yet brittle as glass, crumbling into fragments with the slightest inadvertence of handling or treatment, and the precision of figure requisite to secure good definition is almost beyond the power of language to convey. The quantities involved are so small as not alone to elude sight, but to confound imagination. Sir John Herschel tells us that the total thickness to be abraded from the edge of a spherical speculum, 48 inches in diameter and 40 feet focus, to convert it into a paraboloid, is only 1/21,333 of an inch. Yet upon this minute difference of form depends the clearness of the image, and as a consequence the entire efficiency of the instrument. Almost infinite, indeed, in the phrase of the late Dr. Robinson, must be the exactitude of the operation adapted to bring about so delicate a result. At length, in 1839, 2 specula, each 3 feet in diameter, were turned out in such perfection as to prompt a still bolder experiment. The various processes needed to insure success were now ascertained and under control. All that was necessary was to repeat them on a larger scale. A gigantic mirror, 6 feet across and 54 in focal length, was accordingly cast on the 13th of April, 1842. In 2 months it was ground down to figure by abrasion with emery and water, and daintily polished with rouge, and by the month of February, 1845, the Leviathan of Parsonstown was available for the examination of the heavens. The suitable mounting of this vast machine was a problem scarcely less difficult than its construction. The shape of a speculum needs to be maintained with an elaborate care equal to that used in imparting it. In fact, one of the most formidable obstacles to increasing the size of such reflecting surfaces consists in their liability to bend under their own weight. That of the great Rossi speculum was no less than 4 tons; yet, although 6 inches in thickness, and composed of a material only a degree inferior in rigidity to wrought iron, the strong pressure of a man's hand at its back produced sufficient flexure to distort perceptibly the image of a star reflected in it. Thus the delicacy of its form was perishable equally by the stress of its own gravity, and by the slightest irregularity in the means taken to counteract that stress. The problem of affording a perfectly equable support in all possible positions was solved by resting the speculum upon 27 platforms of cast iron, felt covered and carefully fitted to the shape of the areas they were to carry, which platforms were themselves borne by a complex system of triangles and levers ingeniously adapted to distribute the weight with complete uniformity. A tube which resembled, when erect, one of the ancient round towers of Ireland, served as the habitation of the great mirror. It was constructed of deal staves bound together with iron hoops, was 58 feet long, including the speculum box, and 7 in diameter. A reasonably tall man may walk through it, as Dean Peacock once did, with umbrella uplifted. 2 piers of solid masonry, about 50 feet high, 70 long, and 23 apart, flanked the huge engine on either side. Its lower extremity rested on a universal joint of cast iron. Above, it was slung in chains, and even in a gale of wind remained perfectly steady. The weight of the entire, although amounting to 15 tons, was so skilfully counterpoised that the tube could with ease be raised or depressed by 2 men working a windlass. Its horizontal range was limited by the lofty walls erected for its support to about 10 degrees on each side of the meridian, but it moved vertically from near the horizon through the zenith as far as the pole. Its construction was of the Newtonian kind, the observer looking into the side of the tube near its upper end, which a series of galleries and sliding stages enabled him to reach in any position. It has also, though rarely, been used without a second mirror, as a Herschelian reflector. The splendor of the celestial objects, as viewed with this vast light grasper, surpassed all expectation. "Never in my life," exclaimed Sir James South, "did I see such glorious sidereal pictures." The orb of Jupiter produced an effect compared to that of the introduction of a coach lamp into the telescope, and certain star clusters exhibited an appearance, we again quote Sir James South, "such as man before had never seen, and which for its magnificence baffles all description." But it was in the examination of the nebulæ that the superiority of the new instrument was most strikingly displayed. A large number of these misty objects, which the utmost powers of Herschel's specula had failed to resolve into stars, yielded at once to the Parsonstown reflector, while many others showed under entirely changed forms through the disclosure of previously unseen details of structure. One extremely curious result of the increase of light was the abolition of any sharp distinction between the two classes of annular and planetary nebulæ. Up to that time only four ring-shaped systems, two in the northern and two in the southern hemisphere, were known to astronomers. They were now reinforced by five of the planetary kind, the discs of which were observed to be centrally perforated, while the definite margins visible in weaker instruments were replaced by ragged edges or filamentous fringes. Still more striking was the discovery of an entirely new and most remarkable species of nebulæ. These were termed spiral, from the more or less regular convolutions, resembling the whorls of a shell, in which the matter composing them appeared to be distributed. The first and most conspicuous specimen of this class was met with in April 1845. It is situated in Canes Venatici, close to the tail of the Great Bear, and wore in Sir J. Herschel's instruments the aspect of a split ring encompassing a bright nucleus, thus presenting, as he supposed, a complete analogue to the system of the Milky Way. In the Rossi mirror it shone out as a vast whirlpool of light, a stupendous witness to the presence of cosmical activities on the grandest scale, yet regulated by laws as to the nature of which we are profoundly ignorant. Professor Stephen Alexander of New Jersey, however, concluded from an investigation necessarily founded on highly precarious data of the mechanical condition of these extraordinary agglomerations, that we see in them the partially scattered fragments of enormous masses once rotating in a state of dynamical equilibrium. He further suggested that the separation of these fragments may still be in progress, and trace back their origin to the disruption, through its own continually accelerated rotation, of a primitive spheroid of inconceivably vast dimensions. Such also, it was added, the curvilinear form of certain outliers of the Milky Way, giving evidence of a spiral structure, is probably the history of our own cluster, the stars composing which, no longer held together in a delicately adjusted system like that of the sun and planets, are advancing through a period of seeming confusion towards an appointed goal of higher order and more perfect and harmonious adaptation. The class of spiral nebulae included in 1850 14 members, besides several in which the characteristic arrangement seemed partial or dubious. A tendency in the exterior stars of other clusters to gather into curved branches, as in our Galaxy, was likewise noted, and the existence of unsuspected analogies was proclaimed by the significant combination in the Owl nebula, a large planetary in Ursa Major, of the twisted forms of a spiral with the perforated effect distinctive of an annular nebula. Once more, by the achievements of the Parsonstown reflector, the supposition of a shining fluid filling vast regions of space was brought into, as it has since proved, undeserved discredit. Although Lord Rosse himself rejected the inference that because many nebulae had been resolved, all were resolvable, very few imitated his truly scientific caution, and the results of Bond's investigations with the Harvard College refractor quickened and strengthened the current of prevalent opinion. It is now certain that the evidence furnished on both sides of the Atlantic as to the stellar composition of some conspicuous objects of this class, notably the Orion and Dumbbell nebulae, was delusive, but the spectroscope alone was capable of meeting it with a categorical denial. Meanwhile, there seemed good ground for the persuasion, which now, for the last time, gained the upper hand, that nebulae are, without exception, true island universes, or assemblages of distant suns. Lord Rosse's telescope possesses a nominal power of 6,000, that is, it shows the moon as if viewed with the naked eye at a distance of 40 miles. But this seeming advantage is neutralized by the weakening of the available light through excessive diffusion, as well as by the troubles of the surging sea of air through which the observation must necessarily be made. Professor Newcomb, in fact, doubts whether with any telescope our satellite has ever been seen to such advantage as it would be if brought within 500 miles of the unarmed eye. The French opticians' rule of doubling the number of millimetres contained in the aperture of an instrument to find the highest magnifying power usually applicable to it would give 3,600 as the maximum for the Leviathan of Birr Castle. But in a climate like that of Ireland, the occasions must be rare when even that limit can be reached. Indeed, the experience acquired by its use plainly shows that atmospheric rather than mechanical difficulties impede a still further increase of telescopic power. Its construction may accordingly be said to mark the ne plus ultra of effort in one direction, and the beginning of its conversion towards another. It became thenceforward more and more obvious that the conditions of observation must be ameliorated before any added efficacy could be given to it. The full effect of an uncertain climate in nullifying optical improvements was recognized, and the attention of astronomers began to be turned towards the advantages offered by more tranquil and more translucent skies. Scarcely less important for the practical uses of astronomy than the optical qualities of the telescope is the manner of its mounting. The most admirable performance of the optician can render but unsatisfactory service if its mechanical accessories are ill arranged or inconvenient. Thus the astronomer is ultimately dependent upon the mechanician, and so excellently have his needs been served, that the history of the ingenious contrivances by which discoveries have been prepared would supply a subject, here barely glanced at, not far inferior in extent and instruction to the history of those discoveries themselves. There are two chief modes of using the telescope, to which all others may be considered subordinate. Either it may be invariably directed towards the south, with no motion save in the plane of the meridian, so as to intercept the heavenly bodies at the moment of transit across that plane; or it may be arranged so as to follow the daily revolution of the sky, thus keeping the object viewed permanently in sight, instead of simply noting the instant of its flitting across the telescopic field. The first plan is that of the transit instrument, the second that of the equatorial. Both were, by a remarkable coincidence, introduced about 1690 by Olaus Rømer, the brilliant Danish astronomer who first measured the velocity of light. The uses of each are entirely different. With the transit, the really fundamental task of astronomy, the determination of the movements of the heavenly bodies, is mainly accomplished, while the investigation of their nature and peculiarities is best conducted with the equatorial. One is the instrument of mathematical, the other of descriptive astronomy. One furnishes the materials with which theories are constructed, and the tests by which they are corrected. The other registers new facts, takes note of new appearances, sounds the depths, and peers into every nook of the heavens. The great improvement of giving to a telescope equatorially mounted an automatic movement by connecting it with clockwork was proposed in 1674 by Robert Hooke. Bradley in 1721 actually observed Mars with a telescope moved by a machine that made it keep pace with the stars, and von Zach relates that he had once followed Sirius for 12 hours with a heliostat of Ramsden's construction. But these 18th-century attempts were of no practical effect. Movement by clockwork was virtually a complete novelty when it was adopted by Fraunhofer in 1824 to the Dorpat refractor. By simply giving to an axis unvaryingly directed towards the celestial pole an equable rotation with a period of 24 hours, a telescope attached to it and pointed in any direction will trace out on the sky a parallel of declination, thus necessarily accompanying the movement of any star upon which it may be fixed. It accordingly forms part of the large sum of Fraunhofer's merits to have secured this inestimable advantage to observers. Sir John Herschel considered that Lassell's application of equatorial mounting to a 9-inch Newtonian in 1840 made an epoch in the history of that eminently British instrument, the reflecting telescope. Nearly a century earlier, it is true, Short had fitted one of his Gregorians to a complicated system of circles in such a manner that, by moving a handle, it could be made to follow the revolution of the sky, but the arrangement did not obtain, nor did it deserve, general adoption. Lassell's plan was a totally different one. He employed the crossed axes of the true equatorial, and his success removed to a great extent the fatal objection of inconvenience in use, until then unanswerably urged against reflectors. The very largest of these can now be mounted equatorially. Even the Rossi, within its limited range, has been for some years provided with a movement by clockwork along declination parallels. The art of accurately dividing circular arcs into the minute equal parts which serve as the units of astronomical measurement remained during the whole of the 18th century almost exclusively in English hands. It was brought to a high degree of perfection by Graham, Bird, and Ramsden, all of whom, however, gave the preference to the old-fashioned mural quadrant and zenith sector over the entire circle, which Römer had already found the advantage of employing. The 5-foot vertical circle which Piazzi, with some difficulty, induced Ramsden to complete for him in 1789, was the first divided instrument constructed in what may be called the modern style. It was provided with magnifiers for reading off the divisions, one of the neglected improvements of Römer, and was set up above a smaller horizontal circle, forming an altitude and azimuth combination, again Römer's invention, by which both the elevation of a celestial object above the horizon and its position as referred to the horizon could be measured. In the same year, Borda invented the repeating circle, the principle of which had been suggested by Tobias Mayer in 1756, a device for exterminating, so far as possible, errors of gradation by repeating an observation with different parts of the limb. This was perhaps the earliest systematic effort to correct the imperfections of instruments by the manner of their use. The manufacture of astronomical circles was brought to a very refined state of excellence early in the 19th century by Reichenbach at Munich, and after 1818 by Repsold at Hamburg. Bessel states that the reading off on an instrument of the kind by the latter artist was accurate to about 1/80th of a human hair. Meanwhile, the traditional reputation of the English school was fully sustained, and Sir George Airy did not hesitate to express his opinion that the new method of graduating circles, published by Troughton in 1809, was the greatest improvement ever made in the art of instrument making. But a more secure road to improvement than that of mere mechanical exactness was pointed out by Bessel. His introduction of a regular theory of instrumental errors might almost be said to have created a new art of observation. Every instrument, he declared in memorable words, must be twice made, once by the artist and again by the observer. Knowledge is power. Defects that are ascertained and can be allowed for are as good as non-existent. Thus the truism that the best instrument is worthless in the hands of a careless or clumsy observer became supplemented by the converse maxim that defective appliances may through skilful use be made to yield valuable results. The Königsberg observations, of which the first instalment was published in 1815, set the example of regular reduction for instrumental errors. Since then, it has become an elementary part of an astronomer's duty to study the idiosyncrasy of each one of the mechanical contrivances at his disposal, in order that its inevitable but now certified deviations from ideal accuracy may be included amongst the numerous corrections by which the pure essence of even approximate truth is distilled from the rude impressions of sense. Nor is this enough, for the casual circumstances attending each observation have to be taken into account with no less care than the inherent or constitutional peculiarities of the instrument with which it is made. There is no once for all in astronomy. Vigilance can never sleep, patience can never tire. Variable as well as constant sources of error must be anxiously heeded. One infinitesimal inaccuracy must be weighed against another. All the forces and vicissitudes of nature, frosts, dews, winds, the interchanges of heat, the disturbing effects of gravity, the shiverings of the air, the tremors of the earth, the weight and vital warmth of the observer's own body, nay, the rate at which his brain receives and transmits its impressions, must all enter into his calculations and be sifted out from his results. It was in 1823 that Bessel drew attention to discrepancies in the times of transits given by different astronomers. The quantities involved were far from insignificant. He was himself nearly a second in advance of all his contemporaries, Argelander lagging behind him as much as a second and a quarter. Each individual, in fact, was found to have a certain definite rate of perception, which under the name of personal equation now forms so important an element in the correction of observations, that a special instrument for accurately determining its amount in each case is in actual use at Greenwich. Such are the refinements upon which modern astronomy depends for its progress. It is a science of hairbreadths and fractions of a second. It exists only by the rigid enforcement of arduous accuracy and unwearying diligence. Whatever secrets the universe still has in store for man will only be communicated on these terms. They are, it must be acknowledged, difficult to comply with. They involve an unceasing struggle against the infirmities of his nature and the instabilities of his position. But the end is not unworthy the sacrifices demanded. One additional ray of light thrown on the marvels of creation, a single minutest encroachment upon the strongholds of ignorance, is recompense enough for a lifetime of toil. Or rather, the toil is its own reward, if pursued in the lofty spirit which alone becomes it, for it leads through the abysses of space and the unending vistas of time to the very threshold of that infinity and eternity of which the disclosure is reserved for a life to come. End of Part 1, Chapter 6.